this case here, we have like electrodes, and then we want to read these electrodes, we want to run like classification algorithms, and then we want to actuate a robot. So we are using this part of the brain, like the occipital part of the brain, and that's where the visual cortex is. And we are using a signal called P300 to do that. And then we use also a very cheap headset, like to do this. So this headset is not like very elaborate at all. It's very noisy. So we had to do lots of things like for noise cancellation and things like that. But we are monitoring all those signals there. And there's a huge literature on what signals you should actually try to track. But varies from person to person. So depending on the size of your head, for example, so the position in this is going to change. Depending on how your brain is actually set up, so this is going to change as well. Okay? So what we did, we start like with the literature, and then we decide to do a genetic algorithm to do this, right? So you have like the evolution, and it's going to create solutions, and the solutions are going to be tested. The solutions are going to be used to train like neural networks or SVMs. So that's the way it is done in here. So you start with what we find in the literature, like all those fish there. So then the fitness is determined. So if you're more fit, so you're going to reproduce more. So you're going to have like more solutions. And then we get immigration and mutation, right? Immigration is like for fish is when you have a flood and then fish go like from one pond to another. So this is like the immigration. And mutation is just random. So by this, we want to set like what is the best set of features for a given person, right, to use. And so the example with fish is because my student, so Riley, so he was a biologist. so he worked like he was a geneticist before he became an engineer. So that's why. So that's Riley, and what he's going to try to do, it's to go around that box there. So there are lights that are just blinking there. So the lights, they generate a signal in your brain. So it's called P300, but only if you want that light to blink. So you look at the light, if nothing happens, so nothing happens in your brain. If the light blinks, so there's a signal that pops up in your brain. If another light blinks, but it's not the one that you want to blink, nothing happens in your brain. So this was found because pilots, they had to look at lots of different lights, and then they were using EEG, and then these signals, they were coming up, and then people didn't know. But now we use this for a lot of different things. So Riley now works for Apple, like doing similar things, like for cars, for actual cars, right? The P300 is one of the signals that we can use. There are other signals, like motor signals. So Jacqueline is actually investigating that right now. So how to use other signals to elicit the same type of thing. Another problem is that the lights, since you're moving, so they change the way that potential in your brain works. So that's kind of like a hard problem to do. The robot moves that slowly because the signal is called P300 for a reason. It only happens 300 milliseconds after the event. So you cannot move that fast, right? So because and this system only uses a single signal, like in the brain to do that. Most systems, they use three repetitions, right? So we use a single repetition. And then we got like over 90% accuracy.